OpenGL in JavaFX. OpenGL Open Graphics Library is a cross-language, cross-platform application programming interface API for rendering 2D and 3D vector graphics. The API is typically used to interact with the graphics processing unit GPU to achieve hardware accelerated rendering. In JavaFX OpenGL on Mac Linux embedded. Here you can see OpenGL architecture. GPU is connected to display list and polynomial evaluator and per vertex operations and primitive assembly. Immediate mode is passed from CPU to per vertex operations and primitive assembly, and polynomial evaluator interacts with the display list and polynomial evaluator is connected to per vertex operations and primitive assembly. Per vertex operations and primitive assembly is connected to rasterization. Display list is connected to pixel operations. And pixel operations are connected to texture memory. Pixel operations are going through this path also, and pixel operations are connected to rasterization, and texture memory is connected to rasterization. Rasterization is connected to per fragment operations. Per fragment operations are connected to frame buffer. Frame buffer are connected to is connected to pixel operations. In a geometry pipeline, CPU is connected to vertex per vertex operations and primitive assembly through immediate mode, and per vertex operations and primitive assembly is connected to rasterization. Rasterization is connected to per fragment operations. Per fragment operations are connected to frame buffer. Here you can see a diagram of the rendering pipeline. The blue boxes are programmable shader stages. The OpenGL rendering pipeline is initiated when you perform a rendering operation. Rendering operations require the presence of a properly defined vertex array object and a linked program object or program pipeline object, which provides the shaders for the programmable pipeline stages. Once initiated, the pipeline operations pipeline operates in the following order. One, vertex processing. Under that, each vertex retrieve from vertex arrays as defined by the VAO is acted upon the vertex shader. Each vertex in the stream is processed in turn into an output vertex. Then optional primitive tessellation stages and optional geometry shader primitive processing. The output is a sequence of primitives. Step 2, vertex post processing. The outputs of the last stage is adjusted or shipped to a different locations. Transform feedbacks happens here. Primitive assembly, primitive clipping, the perspective divide, and viewport transform to Windows space. Step 3, scan conversion and primitive parameter interpolation, which generate a number of fragments. Step 4, fragment shader processes each fragment. Each fragment generates a number of outputs. Pre-sample processing, including but not limited to scissor test, stencils test, depth test, blending, logical operations, right mask. Vertex specification. The process of vertex specification is where an application sets up an ordered list of vertices to send to the pipeline. These vertices define the boundaries of a primitive. Primitives are basic drawing shapes like triangles, lines, and points. Exactly how the list of vertices is interpreted as primitives is handled via a later stage. This part of the pipeline deals with the number of objects like vertex array objects and vertex buffer objects. Vertex array objects define what data each vertex has, while vertex buffer objects store the actual vertex data itself. A vertex data is a series of attributes. Each attribute is a small set of data that the next stage will do computations on. While a set of attributes do specify a vertex, there is nothing that says that part of a vertex attributes set needs to be a position or normal. Attributes data is entirely arbitrary. The only meaning assigned to any of it happens in the vertex processing stage. Vertex rendering. Once the vertex data is properly specified, then it is rendered as a primitive via a drawing command. Vertex processing. Vertices fetch due to the prior vertex rendering stage being they are processing here. Vertex processing stages are almost all programmable operations. This allows user to code to customize the way vertices are processed. Each stage represent different kinds of shade operations. Many of these stages are optional. Vertex shader. Vertex shaders perform basic processing of each individual vertex. Vertex shaders receive the attribute inputs from the vertex rendering and converts each incoming vertex into a single outgoing vertex based on an attribute arbitrary user-defined program. Vertex shaders can have user-defined outputs, but there is also a special output that represent the final position of the vertex. If there is no subsequent vertex processing stages, vertex shaders are expected to fill this position with the clip space position of the vertex for rendering purposes. One limitation on vertex processing is that each input vertex must map to a specific vertex output vertex, and because vertex shader invocations cannot share state between them, the input attributes to output vertex data mapping is one-to-one. That is, if you feed the exact same attribute to the same vertex shader in the same primitive, you will get the same output vertex data. This gives implementations the right to optimize vertex processing. If they can determine if they can detect that they are about to process a previously processed vertex, they can use previously processed data stored in a post transform cache. Thus, they do not have to run the vertex processing on that data again. Vertex shaders are not optional. Tessellation. Primitives can be tessellated using two shader stages and a fixed function tessellator between them. The tessellation control shader TCS stage comes first and determine the amount of tessellation to apply to a primitive, as well as ensuring connectivity between adjacent tessellated primitives. The tessellation evolution shader TES stage comes last, and it applies the interpolation or other operations used to compute user-defined data values for primitives generated by the fixed function tessellation process. Tessellation as a process is optional. Tessellation is considered active if a TES is active. TCS is optional, but TCS can only be used alongside a TES. Geometry shader. Geometry shaders are user-defined programs that process each incoming primitives, returning 0 or more output primitives. The input primitives for geometry shaders are the output primitives from a subset of primitive assembly process. If you send a triangle stripped as a primitive, what the geometry shader will see is a series of triangles. However, there are a number of input primitives, primitive types that are defined specifically for geometry shaders. These adjacency primitives give GCs a larger view of primitives. They provide access to vertices of primitives adjacent to the current one. Output of a GS is 0 or more simple primitives, much like the output of primitives at assembly. The GS is able to remove primitives or tessellate them by outputting many primitives for a single input. GCS can also tinker with the vertex values themselves, either doing some of the work for vertex shader or just to interpolate the values when tessellating them. Geometry shaders can even convert primitives to a different types. Input points primitives can become triangles, or lines can become points. Geometry shaders are optional. Vertex post-processing. After the shader based vertex processing, vertices undergo a number of fixed function processing steps. transform feedback, the output of the geometry shader or primitive assembly are written to a series of buffer objects that have been set up for this purpose. This is called transform feedback mode. It allows a user to transform data via vertex or geometry shaders, then hold on to that data for use later. The output the data output into transform feedback buffer is the data from each primitive emitted by this step. Primitive assembly. Primitive assembly is the process of collecting a run of vertex data output from the prior stage and composing it into a sequence of primitives. The type of primitive the user rendered with determines how this process works. The output of this process is an ordered sequence of simple primitives, lines, points, or triangles. If the output is a triangle strip primitive containing 12 vertices, for example, the output of this process will be 10 triangles. If tessellation or geometry shaders are active, then the limited form of primitive assembly is executed before these vertex processing stages. This is used to feed those particular shader stages with individual primitives rather than a sequence of vertices. The rendering pipeline can also be absorbed at this stage. This allows the use of transform feedback operations without having to actually render something. Clipping. The primitives are then clipped. Clipped mean that primitives that lie on the boundary between the inside of viewing volume and outside are split into several primitives such that the entire primitive lies in the volume. Also, the last vertex processing shader stage can specify user-defined clipping operations on a per vertex basis. The vertex positions are transformed from clip space to window space via a perspective divide and viewpoint transform. Face culling. Triangle primitives can be culled, that is discarded without rendering based on the triangle facing in the window space. This allows you to avoid rendering triangles facing away from the viewer. For closed surfaces, this triangle would naturally be covered up to by triangle facing the user, so there is never any need to render them. Face culling is a way to avoid rendering such primitives. Rasterization. Primitives that reach this stage are then rasterized in order in which they were given. Result of rasterizing a primitive is a sequence of fragments. Fragment is a set of state that is used to composite final data for a pixel or sample if multisampling is enabled in the output frame buffer. The stage for this fragment include its position on the screen space, the sample coverage if multisampling is enabled, and a list of arbitrary data that was output from previous vertex or geometry shader. This last set of data is computed by interpolating between the data values in the vertices for the fragment. The style of interpolation is defined by shader that outputted those values. Fragment processing. The data for each fragment from the rasterization stage is processed by a fragment shader. The output from the fragment shader is a list of colors for each of the color buffers being written to a depth value and a stencil value. Fragment shaders are not able to set the stenciled data for a fragment, but they do have control over the color and depth values. Fragment shaders are optional. If you render without a fragment shader, the depth and stencil values of the fragment get their usual values, but the value of all of the colors that a fragment could have are undefined. Rendering without a fragment shader is useful when rendering only a primitive default depth information to the depth buffer, such as when performing occlusion query test. Pre-sample operations. A fragment data output from the fragment processor is then passed through a sequence of steps. First step is a sequence of culling test. If the test is active, the fragment fails the test. The underlying pixels samples are not updated usually. Many of these tests are only active if the user activates them. The tests are pixel ownership test, fails if the fragment's pixel is not owned by the OpenGL, if another window is overlapping with the GL window. Always passes when using a frame buffer object. Failure means that pixel contains underlying undefined values. Scissor test. When enabled, the test fails if the fragment pixel lies outside of the specified triangle of the screen. Stencil test. When enabled, the test fails if the stencil value provided by the test does not compare as the user specified against the stencil value from the underlying sample in the stencil buffer. Note that stencil value in the frame buffer can still be modified even if the stencil test fails, and even if the depth test fails. Depth test. When enabled, the test fails if the fragment's depth does not compare as the user specified against the depth value from the underlying sample in the depth buffer. Through these are specified to happen after the fragment shader. They can be made to happen before fragment shader under certain conditions. If they happen before fragment shader, then any culling of the fragment will also prevent fragment shader from executing this saving performance. After this, color blending happens. For each fragment color value, there is a specific blending operations between it and the color already in the frame buffer at that location. Logical operations may also take place in lieu of blending, which perform bitwise operation between fragment colors and fragment frame buffer colors. Lastly, the fragment data is written to the frame buffer. Masking operations allow the user to prevent writes to certain values. Color, depth, and stencil write can be masked on and off. Individual color channels can be masked as well. Here you can see a vertex specification is connected to a text shader. Vertex shader is connected to tessellation. Tessellation is connected to geometry shader. Geometry shader is connected to vertex post processing. Vertex post processing is connected to primitive assembly. Primitive assembly is connected to rasterization. Rasterization is connected to fragment shader. Fragment shader is connected to pre-sample operations. You can see programmable shade stages here: vertex shader, tessellation, geometry shader, and fragment shader. As an example, we can consider this code segment to make sure the JavaFX is using OpenGL Prism backend. So here ES2 is used. As example 2, we can consider this JavaFX 8 command line option. Prism order this implies which driver to use. Here ES2 OpenGL ES 2.0. As an error example, we can consider this, and here you can see gog.opengl.gl gl drawable imply impl.unlock surface at gog.amp.opengl.gl context impl.release, etc. As an error example 2, we can consider this error occurred in environment with Raspberry Pi 2 with Ubuntu 14.04. libegl warning: DRI2 failed to authenticate, failed to create EGL context graphics device. Initialization failed for ES2. Error initializing quantum renderer. No suitable pipeline found java.lang.runtime exception.